We're ready? Oh, right, okay. All right, well, good morning everyone, welcome, thank you for coming, and sorry about the unusual time for this talk, but it's great to see so many people here. It's a real pleasure to introduce Barrett, who's come all the way from the University of South Australia. He's been working on a postdoc position with Mark Billinghurst, is that right? Yeah. Many of you probably know Mark in his work. So it's really great to welcome him here, and he's going to give us an overview of the research that he's been doing. So welcome Barrett, and thank you for coming.
Great, thanks John for inviting me. I'm really glad to be here today and to share my work with everyone. First I'm going to just give a little brief background about myself. So John mentioned I'm currently a postdoctoral research fellow at the University of South Australia in the Empathic Computing Lab. Prior to that I completed my PhD at the University of Manitoba, and during my studies I spent a couple of internships at Autodesk Research, and I also spent one summer as a visiting research in Austria at the University of Applied Sciences of Upper Austria at their Media Interaction Lab. I just want to share a few of the milestones that I passed on my way to get here today. So at one time I studied classical guitar and electroacoustic music, and before I graduated I put together a concert of my own compositions, which was exciting, and as I was finishing my music degree I discovered computer science. As an undergraduate, I got to participate in Robo Cup, and you can see me here. I got to do these robot soccer competitions with these little robots that had the old-timey Nokia phones as brains and computer vision and everything. And after I graduated, I spent a couple of years working in industry, and I returned to the University of Manitoba to study human-computer interaction, where I discovered spatial interaction, which is related to the talk that I'm going to give today. So, if you've ever seen the recent BBC take on Arthur Conan Doyle's character Sherlock Holmes, then you may have seen him going to what he calls his mind palace. Now, Sherlock's mind palace is not a purely fictional construct, but this is actually a real spatial visualization technique that dates back to ancient Greece and is actually used by people who do memory competitions who can memorize thousands of objects. So this technique works by associating specific memories with physical locations. For instance, your favorite armchair in your living room. And this technique takes advantage of our kind of natural human ability to kind of make mental models of space and to make spatial maps and to navigate our environment. Oops. And we actually use similar spatial techniques in the design of user interfaces for computers. So for instance, in the common desktop computer metaphor, we use spatial memory to quickly be able to find and retrieve things in the taskbar, or items on the desktop, or items within hierarchical menus. Now some researchers have explored how to make computer desktops even more like the physical world. For instance, by putting documents into virtual 3D spaces, or by adding physical simulations to desktop environments. And more recently, there's some research studies have shown that there are actual benefits of spatial interaction. So for instance, so spatial interaction can improve the performance of some tasks. For instance, using a mobile phone, moving it in space to quickly switch applications, or using the space around a mobile device to kind of mentally organize space and expand the interaction space. Or some studies have looked at analytic tasks on large wall displays and found that this actually improves over the same task on a desktop display. So my work explores spatial interaction with kind of new next generation technologies such as augmented and virtual reality, wearables, and the Internet of Things. And this talk is about using these in the context of immersive analytics. So immersive analytics, I probably don't need to define it here, but it's kind of, you could say it's an emerging field that applies new immersive technologies to help people kind of explore information and help them to make decisions, in a nutshell. So these immersive technologies are going to be particularly relevant for certain types of tasks. So just to give a couple of examples, 3D visualization. So this is an example from a project I did a few years ago where you have a software visualization. So this is an existing kind of clustering that they do between software files and testing files. And they want to see what are the relationships of these. It's called a co-change relationship. When are these changed at the same time? The problem is this just gives you one snapshot of the entire software project over its entire history. What if you want to see how this evolves over time? So you can add a third dimension to visualize this, make kind of what's called a space-time cube. And you can use spatial interaction to visualize this in an immersive system. And now you can actually walk around this complicated structure and look at it from different angles. This will help you to give a better understanding of that structure. Another example is when immersive technologies are useful is when the spatial context is particularly important to the task. So for instance, this worker has a tablet, and we have new technologies like tablets and networking technologies that allow somebody to do this kind of situated task. But if you use something like mixed reality, you can actually overlay that information directly onto the environment, onto the surroundings, and this might provide a richer understanding of that information and help you understand the task a little bit better. So the goals of my research are essentially to facilitate understanding of information and complex data sets, to support human-in-the-loop decision-making, and really to move computing into the physical world and away from the limitations of flat screens that are very common now. So for the rest of this talk, I'm going to just give an overview of my previous work. I'm going to briefly touch on some of the current projects that I'm doing at the UniSA, and I'm going to give an overview of my future research plans. So I'm going to talk about 3 specific projects that are related to leveraging spatial interaction in immersive environments. So the first one of these is about spatial layouts, and this is based on some work that I presented at CHI a few years ago. And this is really about how to build a user interface using an augmented reality display to try and support situated tasks. So one of the questions that we asked is, if you have these benefits of being able to move and look at data by physically navigating in the environment, do these advantages of spatial interaction still hold if you have the relatively small field of view of a see-through head-worn display? So we actually emulated this field of view in a cave environment. So it's about a 40 degrees field of view, which is a little bit wider than what the HoloLens has today. And this gives us kind of a low latency environment, high precision tracking to be able to look at the human factors of this problem. And we tested some participants with an analytic task. So the participants had to look at these different information interfaces. They had to piece together some information and kind of solve a puzzle and answer a question. And it turns out that if people could use their head motion to switch displays, they were about 40% faster than using 2 different baseline techniques with abstract navigation. That would be more kind of view-fixed methods that are similar to what we do on cell phones now. There's a very clear advantage of this spatial interaction. And then we wanted to look at also how to integrate these layouts into the physical environment. So if I come to work, I might want to pin my applications on the wall, and then before I go for lunch, I can go around and collect them and bring them out with me. So we looked, in the next project, I looked a little bit more closely at how this would work. So we wanted to look at one of the key factors of this project was this spatial constancy. So if I'm moving between different environments, if I have this kind of expected layout of my applications, if my calendar is down on my lower right when I'm in my office, and then later I go to my living room, I expect to find or hope to find the calendar on my lower right, so that I know you can use my spatial memory to quickly find that application when I want it. So we looked at trying to keep this, maintain this layout of these different applications, but also respecting the kind of physical structure of the environment that you're in, so that you can move between rooms and you have this kind of unpredictable structure. So what we did To implement this is we took a scan of 2 different environments using Connect Fusion. So this is the office kind of setup that we had here. Created a 3D model, and then we took an image, just a single image, and we added a saliency map under this image. So visual saliency algorithms typically basically try to predict what is important to the human eye. So this is a prediction of that using one of many available saliency algorithms. And then we did a calibration between these. So this calibration allows us to do a query of any point in the 3D model and to be able to find the saliency for that region. So you can see that the red areas in this image are very highly salient, so we want to avoid putting stuff in front of our computer screen and on the keyboard, and the green areas are low salient. So these are kind of basically empty spaces where we can kind of put things and they won't conflict with anything in our surroundings. And then we did a random walk algorithm to kind of take this body-centric layout and project it onto the room, and this is what it looks like in 2 different environments. So again, we're trying to respect the environment, but also maintain a similar layout structure so that we can take advantage of this spatial memory to find our application. So this is what it looks like through a BT200 Barrett display. This is using a Vicon for head tracking, but you can see here there's the calendar on my lower right, and on the offices there's the map application, and there's the calendar on my lower right in the office environment. So this set of projects kind of looks at how we can help support analytic tasks by distributing information into the environment. Next, I'm going to talk about a project where we look at how to interact with environments that already contain their own sources of information. So a brief introduction to the Internet of Things. So this is essentially a vast network of interconnected smart objects, a huge growing network, and it has several useful purposes. For instance, collecting data for analytics, helping us to manage energy consumption, and predicting equipment failure, just to give a few examples. But as this network of smart objects continues to grow, the question is, we ask, so this project is how are we going to manage the relationships between this huge array of objects? So we took some inspiration from these kind of visual programming languages that use things like shape and color to try and help make programming accessible to non-experts. So people who don't know how to program can kind of interact with these things. And both of these languages have applied these concepts to Internet of Things and embedded systems. So one limitation of these languages is that there's a disconnection between the digital artifacts and the objects, the physical objects that these represent in the real world. But there are some situations where this spatial context, of course, is very important. So you can imagine a maintenance worker who's looking through a smart building, and if they're trying to find the source of an anomalous sensor reading, it may help them to be able to see the physical surroundings. For instance, if they can see a water leak in the building while they're examining the sensors. Or a building manager who's interested in saving energy may be interested to know, it will help them to understand all the locations of their sensors and actuators within that environment to help them do their task. So this is a project I did while I was at Autodesk Research. Last year I just presented this a few months ago at GI, and we built a prototype called Ivy. So Ivy is what we call a situated visual programming environment, and this is used for authoring constructs, understanding connections between smart objects, and visualizing data flow, all within a virtual representation of the environment. So we use virtual reality so we could explore multiple different environments, has a wide field of view, and these controllers to help us so we don't have to focus as much on the input technology and focus on the interface. So Ivy users build programs using these virtual logic constructs. So for instance, you have a virtual port. This represents a virtual interface to that smart object, to its sensors and actuators. A trigger is kind of the most fundamental programming construct in IoT. This is like an if-then operation. Then you have a number of different functions for things like aggregating, filtering, converting data types. And we have this cloud node, which represents a connection to a distant virtual server. Now these nodes are connected using these virtual tubes. So the tubes connect those in a top to bottom fashion. And you can see that each end of the link is colored to the node at the opposite end to help you understand what it's connected to. And programs that you can build with Ivy are fully functional. So we used actual input from real sensors. So we used Texas Instruments TI tags to give us some sensor input data, and we connected our programs to actual output from fidgets actuators. And we also wanted to look in this project at visualizing data flow. So we represented the data using these virtual particle clouds. So the particle color represents the type of data. For instance, yellow is light sensor data, red is accelerometer data, and the particle size represents the value of that data. So as the programming is running, you can actually see values flowing through the programming, and you can see them change in real time as the sensor values change. So I'm going to show you a simple example program. So this is kind of a test environment that we built. So you can see a number of smart objects around the room and on the table here. So I'm going to start by constructing a trigger node. So I'm going to place that here. And then I'm going to grab my linker tool, and I'm going to connect the Windows light sensor, and I'm going to connect that to the trigger node. And the trigger has a preset function that I can use, and this is basically a threshold. If there's the light is over a certain lumens value, it's going to send a trigger. So then I'm going to connect the output of the trigger node to this fan on the table. So this means when there's a lot of light, it's going to trigger the fan, and the power is going to come on, and it's going to cool me off. So you can see when I run this program, and I shine a light on this sensor tag, you can see the values turn from low to high, coming from the sensor, and then this is going to trigger the actual physical fan to turn on in the real environment. So here's another example that we built. This is a scenario, say you have a museum environment where the manager wants to kind of remote in and look at these foot traffic sensors. So they can look from a distance without going to the museum. They can see how many people are in the museum. These are averaged into this trigger node, which activates this central exhibit. So you can run the program remotely, view the data visualization, see how many people are in the museum, and you can choose the particular server that you want to send your data to for later analysis. I won't go into too much detail about this, but we built a suite of debugging tools. So like any integrated programming environment, you want to be able to do things like pause and step through the program and see a specific state and so forth, so you can try and identify bugs. In this case, we just kind of slowed down the visualization so you can see it kind of changing from node to node a little bit more slowly than actually happens when the programming is running, just so you can understand the flow a little bit better. Okay, so that project showed how spatial interaction can help us to understand data within a spatial context. Next, I'm going to look at how to address some of the limitations of spatial interaction. So this is, I presented this last year at SUI, which is the symposium on spatial user interaction. And this works with the kind of the window layout context that I talked about in the first project. So in immersive environments, there are some advantages to using what we call natural input methods. So I want to use my hands to be able to grab things and interact with them like we interact with objects in the real world. So this is very appealing because it's intuitive and it can be very useful, but there are some specific limitations. For example, fatigue, if I'm waving my arm around too much, or if I'm acting without a tangible surface, then there's very well-known limits of precision. So we want to look at how we can support these multi kind of window layouts on a couple of different levels. So on the one hand, we may be able to want to manipulate layouts. We can use this natural input techniques to say put two visualizations side by side so that we can compare them. But we also want some sort of precision so we can interact with the data and select small data points within those visualizations. So we looked at a combination of using a head-worn depth camera on top of this Muverio display in combination with this small ring device. So the depth camera allows us to track the hands for natural input, and the ring device gives a small surface so we can do some very precise manipulations. So we explored this interface through this analytic task of a hotel search where you have a few different windows. You have a preview window, find a hotel, you have a map with some map pins on it, and you have a filter panel where you can do some filtering of the different hotels. These are what the three windows look like through the Muverio display. And so this is an example of some direct manipulation. So I can kind of do a virtual tap on these windows. I can select some of the map pins, select a region on the map, or select one of the specific filter controls. But we can also do some things that you can't do with the camera alone. So for instance, the camera's good at tracking the position of the hand, but tracking the orientation of the hand is actually very difficult with hand tracking that's available now. But the ring has an IMU that we can use to measure the rotation of the hand. So together, by combining both of these different input sources, we can control this window in 6 degrees of freedom. So I can grab it and manipulate it, rotate it, as well as translate it. We can also combine these kind of sequentially. So I can select one of the filter controls, and then I can kind of put my hand into a relaxed position by my side where I can manipulate the filter control, and I can look over at the map and see which pins are selected by using my head motion. So here's another example where, so similarly, the IMU, if we want to have a ray pass, the ring can determine the orientation of the ray, but the ring doesn't know the hand's position. But with the camera, we can track the hand position, so this tells us where to put the origin of the ray. Otherwise, we'd have to fix it somewhere. So I can use this ray to turn on the ray. I can select one of the windows, or I can select a region within the map and select a set of the map pins. So here's another example of an analytic kind of manipulation. So I can select a region on the pin. So this interaction is not very precise. I can't select a single point with the ray or with my finger, but I'll just back up and maybe show that again. So if I tap on the, no, it doesn't want to play, sorry. So if I tap a region on that map, it'll select a subset of the pins, and then I can use the ring device kind of again in a relaxed position to cycle through those selected pins and then look at the different previews as they appear on the adjacent window. So both of these projects were part of my PhD thesis work, and we also published a summary of this work in Computer Graphics and Applications Journal, and we're also invited to present a version of this paper at a special session of IEEE Viz in Baltimore last year. So altogether, these projects, hope I've shown a variety of ways that we can kind of interact with information in the physical world. Leaving that aside, I'm just going to touch briefly on a few of my current projects. So the first one I'm going to talk about kind of picks up where I left off. It builds on some of my previous work. Again, we're looking at these limitations of spatial interaction and hand gestures. So in this work, we're looking at what we call micro gestures, so very small motions of the hand. This is one way to try and reduce fatigue, is to limit the size of the gesture that you're making, and also can potentially give us some precision with small gestures. So we're working with this Google Soli prototype. It's essentially a miniature radar, so it works on the same principles as radar that they have at the airport, except it's a much higher frequency and is designed to detect hands, so it can detect very fine motions on a sub-millimeter level. So very small micro gestures, but it doesn't give you a lot of information about the hand pose. So we tried pairing this with a leap motion, which gives you some of that pose information. We combined this into this 3D printed housing, and we made kind of this belt interface. So similar to the previous phase, I can interact with this with my hand in a lowered position, kind of relaxed. And we built this demo with a docking task. So suppose I have this 3D object and I want to manipulate it, put it in a very specific position. So the docking task allows us to kind of test this out to see how it works. So this is an example of, with hand tracking alone, I can kind of use kind of this natural input technique. I can grasp that object and I can try and put it into this docking position. And you can see that I can get it very close, but it's quite difficult to get the rotation quite right. Especially if it's in this position, the hand tracking just doesn't work that well. But if we combine these devices, so here's the picture of the implementation on the HoloLens. So you can see we have this head-mounted camera again, and the side device. So using the leap-solid combo, what we can do is we can map different controls to the different fingertips. So in this case, we map the different axes of translation to each of the 3 different forefingers, and we can add 3 additional controls to, if I touch the side of my finger, this gives me some controls to control the rotation of the object. So now I have 6 degrees of freedom that I can use with one hand. So here's me just showing each of the different axes of translation. I tap each finger. So this is mainly the leap doing the work for this part, but the Soli allows us to actually detect very fine precision motions on all of these degrees of freedom. So here's the docking task again. So I can initially use direct manipulation. It's a very quick, easy way to put the object generally where I want it. And now I can use some fine tuning to try and have some fine control over exactly where I want to put this object. And voila. Also at the Math Computing Lab, we're working a lot with physiological sensing. So for instance, electroencephalogram, electrocardiogram, galvanic skin response gives us some information about the physiological state, perhaps the mental state and emotions of users. I'm working with some students right now on some projects that are focused on sharing emotion in remote collaboration. So people using VR displays and AR displays, how can we share their kind of physical and emotional state with other people? And I'm also doing some collaboration with the Wearable Computing Lab and the Cognitive Neuroscience Department at the University of South Australia, and we're looking at things like the cognitive load of augmented reality. So can we figure out how difficult this is to use? And this has many implications in interface design and the adoption of augmented reality in the future. So just briefly, another project I'm working on is called the Gaze Browser. So this is focused on using eye tracking sensors. So if you haven't seen this short film called Hyper Reality, I recommend looking it up. It's a lot of fun. It's basically a short film that presents a very dystopian view of the future of augmented reality. And it's really basically an over-the-top look at an actual real problem. So in the future, you can imagine if augmented reality becomes ubiquitous, people are going to pin things, place augmentations in a lot of our home and work environments, and there's going to be a lot of clutter that we want to sift through. So we can imagine that all of these augmentations or annotations are kind of collapsed, and we're looking at using gaze so that you can quickly kind of browse over these augmented objects so you can see a little bit of information about them. And we're looking at other gaze-based techniques, so you can do things like selection, and say if you have a menu, you want to do a little bit further interaction with a particular object. So I'm going to talk about a little bit about where I expect to take immersive analytics in the next, say, 2 to 10 years. So one thing, oops.
I think that was me, sorry.
Okay.
No, it wasn't you, Bruce.
There we go.
Normally it's me.
So one thing that I'm interested in is what I call room scale visualization. So right now we have visual analytics in kind of purpose-built rooms where you have a large display and you have a lot of smaller displays all distributed around the room, and people are collaborating on these tasks and solving problems. But imagine with immersive technologies, you can actually fill up as much of the room as you want with data, not just the surfaces, but the interstitial space in between. So this is freely configurable, and you can arrange things freely where you want them for a specific task, so it's very flexible. So there's a lot of kind of immediate research questions that we can ask about this type of environment. So one that's kind of still an open question is, what are the benefits of immersion and what are the benefits of spatial interaction? When do we use 2D interfaces versus 3D interfaces? So when is it good to use what type of visualization? Information visualization is kind of notoriously difficult to evaluate, so this is going to require some new metrics and some new research methods to try and answer these kind of problems. So for instance, we can use EEG to try and detect the cognitive state of the user to see if this is more difficult or less difficult. We can use something like eye tracking to kind of predict the salient points of an interface and try and use some of these, perhaps some of these physiological methods to evaluate these. Once we kind of learn more about that, we can look at more kind of interesting ways to combine 2D or 3D. So maybe you have 2D visualizations that pop out into 3D, and you use each of them for their best specific purposes. And of course, there's a lot of work to be done about collaboration. So how do you configure these environments? Where are people going to place things in this environment, maybe using their spatial memory to retrieve objects, and things like a user's sense of territoriality over specific regions of the room, and all of those kinds of questions. There's still lots of work to be done in interaction and immersive environments. So this is a far from solved problem. When are these, again, similarly to before, is natural interaction useful and when is it not useful? When do we need other types of interaction devices? When can we use hypernatural interaction? So when can we actually go beyond what you can actually do in the natural world? Of course, this will be very focused on analytics operations. So we want to look at things like scaling, filtering, aggregation, selecting very small data points, or maybe doing group selection. So for instance, how do you select a group of points from a 3D volume and get the points that you want and don't select points that you don't want? We can look at novel interaction devices, tangible widgets, haptic feedback, etc., maybe special purpose devices for particular types of visualization. Looking a little further on, we can work on, so situated analytics. A lot of you are familiar with this. It's kind of a subset of immersive analytics. In the next, say, 5 years or so, there's going to be a lot of focus on industry in this kind of field. So things like this mobile worker want to be able to go on site, but they want to take some of the control room with them, so to speak, so they can see the information that they need while they're doing the task. So we want to move towards deploying actual functional systems that people can use on actual work sites and use in these real settings. So there's a lot of sub-problems before we get there. We need things like very small or wearable interaction devices that people can use easily in these type of environments that they can use for interacting with visualizations. We need to look carefully at the design of visualizations. We have things like safety concerns. We don't want to cause somebody some safety issues on the job site. We want to prevent distraction, and it's very, very different from building immersion in a controlled setting. And then as technology matures, we can apply a lot of these concepts to social visualization. So in the social situation, we can build these kind of distributed interfaces, but they have to be, people are very particular about what they want to share. So the context of where they are work, or are they at home? Is it a public or private sharing situation? Who are they sharing with? What time is it? All of these matter in what people want what kind of visualizations people want to share. So we want to build some of these distributed interfaces for multi-user immersive applications in social settings. And this is more of a long-term goal, but we want to think about something we call the pervasive information layer. So we want to view information as kind of an essential feature of a built environment, very much the same way we look at lighting and building materials today. In the future, we're going to look at information in a very similar way. It's just going to be there, it's going to be part of the building, and everybody's going to use it quite regularly. So we want to look at how to incorporate this information layer at design time, whereas in a lot of the work I'm talking about, we're trying to kind of retrofit existing environments and overlay information on these, but how can we build this kind of at design time? So we need some guidelines to inform designers, how do we build this information layer, what's appropriate and what's not appropriate. And we need to build some tools for designers to perhaps integrate this information layer into existing design software so they can build this into their building plans. So I just want to acknowledge my collaborators in all of this work. So I've worked with a lot of people in the research that I've shared today, and I'm going to continue to expand my research network. And there's many potential opportunities to collaborate at Monash, within SensiLab, within the Immersive Analytics Group, and as well as both within the Faculty of Information Technology and in other faculties of the university. Immersive Analytics is, by its nature, it's a very collaborative, multidisciplinary field. And lastly, I just want to mention some of the places where my work has gained attention. So in particular, engineering.com just very recently published an article about the Ivy project that I shared with you today. And that brings my talk to a close. It was a real pleasure to share my work with everyone here. And thanks you very much for listening, and I can answer your questions.
Okay, thanks, Barrett. We'll take some questions now. Tim.
So, Barrett, I really like the situated programming system, but even before you showed the hyper reality example, I was already starting to think it would get cluttered very quickly, and some of your examples were already starting to get cluttered. What have you thought? What sort of techniques have you thought about using to reduce the clutter?
Well, I think it's very much based on, so I based that programming language a lot off of Max, or it's called Max MSP, which is a multimedia design language. So I would probably approach it in a similar way. So they have a feature in there so you can do encapsulation. And so it's very easy to build unstructured nested programs in Max, and similarly here. So you basically want to think in modular structures. So if you build a certain structure, you want some feature to encapsulate this into an object that represents that subsystem, and then you can have ports to kind of plug into that and outputs from that subsystem. And then over time, you can build kind of a library of these subsystems so that you can reuse these. You can grab a subsystem and you can place it here, and then you can just plug some sensors into it and have the data come out, and you can build some things very quickly that way.
So I think that's definitely probably the most important first step. But also, what about using the environment? So it seemed like a lot of the wires and things were coming straight through the middle of the space, and
Yeah.
were right in front of your face. Do you think you could kind of dynamically reconfigure that?
I think so. I mean, in some ways, it's a very naive implementation. So we have these nodes, and you just have a very basic. There's the tube just kind of connects itself, but there's no thought into about where the tube is going. So if you've seen some of the work from like the Vislinks project from Sheila Carpendale, where you have these links between visualizations. There's an interesting paper from Igor Schmalstein's lab where he looks at how to, on a computer desktop, how do you make these links kind of avoid salient areas of the interface. So you kind of route them around information, or you make them transparent. So you can add some features in to make the links a little bit more intelligent. So maybe they go around the edge of the room or something, or follow surfaces and things like that. The big picture, I think, it kind of depends on the use case. I figure this is really aimed at non-experts. So I think a lot of these programs will be relatively not overly complex. So the real goal is to show the relationships between objects. And I don't know if people will necessarily be building really complex programs in this kind of situation. You want to really have a lot of the complex stuff is built maybe on a desktop. You do all the low-level programming, you have some preset functions, and now you just want to go in and do the very high-level stuff. You say, okay, I want that thing to do this, and to that thing, or I want to see this information about that object for predictive maintenance, or these kinds of very high-level operations. But right, there's lots of areas to build on that work.
So just regarding the docking example, with using the small finger interactions for rotation and translation and things, did you just focus on accuracy for those experiments? Did you actually look at how intuitive it was to use when compared to desktop interaction? Because it seems like it would be quite a steep learning curve to learn what actions translate to which degree of freedom and so on.
So which ones map to what? Yeah, you can see I've added some kind of nodes to those to kind of give some hints about which axis is which. So this, first off, this isn't meant to really compete with the desktop interface. So this is meant for situations where you don't want to use a desktop computer. So say if you have a collaborative visualization and you want to stand in the group and look at something or build with something, or if you're in some situation where it's a mobile worker, you don't have a desktop, things like that. So I think beating the mouse at any of this is a super long-term goal, and it's not going to happen soon. And if you can beat the mouse with any spatial interaction technique, you're going to get a PhD on a silver platter, so to speak. But what we're really looking at is how to. So it's not based on the intuitiveness. This is part of a design space exploration. So I'm still working on this project, actually. What we're trying to do is just explore a variety of different techniques. So it's really an exploratory project. We're looking at what kind of things can we build that use micro interactions, but not just use micro interactions, but integrate these in with other types of spatial interaction. So we want to look at when can you use things like direct manipulation. When is this? How can we use that to its best ability, and how can we use other input techniques to their best ability? So kind of combining different types of interaction in different ways. So another project that I'm working on right now is kind of a virtual marionette. So you can combine some micro interactions by wrist melting the sole. You can detect some small motions, but you can also track the hand motion, so you can control the movement of the puppet. Maybe you can use some triggers to trigger certain animations of the puppet, but also have some very fine control over specific features of the marionette. So actually very similar to the way people use real marionettes, but we can maybe go a little bit beyond that and do some things that they can't do. But it's just looking at examples of how we can use different sensors. So these are really meant to be optimized anyway, but it's just exploring the design space of different types of gesture interaction.
Great. Thanks for this. It was super interesting. Still on the topic of interaction with device and selection task in photos, for example. That's a very interesting topic and very core, I think, at the moment with immersive visualization and everything. And you're talking about, direct manipulation, for example. Let's say we want to draw a bounding box around 3D scatter blocks, so we have like the benefit of using spatial interaction to draw a quick bounding box. But then I want to do a more precise range selection, for example. So it's kind of this weird situation where I want to have like mid-air interaction, and then suddenly I want like a tangible surface, or like a cursor, or a physical cursor, or something like this too. Have you thought about like the ultimate device, or because it's kind of it's kind. I mean, it's a silly question, but it's right in your design space questions.
Yeah, no, it's very open. I think we're a long way from having a device with interaction method for AR or VR. There's there's new controllers coming out on the market, like the Oculus thing they introduced a couple of years ago, and tried to implement kind of grasping type gestures with the controller. I haven't actually tried it, but I'm skeptical. I think there's a lot of other research areas we can apply to this. So more multimodal interaction, so incorporating voice commands, like eye gaze, maybe restrict what you're looking at. So you can maybe use, so not just a bounding box, but what if you want to do a 3D lasso selection, where it's even more complex? Maybe you can use eye gaze to try and predict what are the salient features that you're trying to select, or having more richer gestures to select a region. And then I think, and so I'm very interested in looking at things like new devices and wearables that you can have easily on hand.
Yes.
So, and then this becomes even more of an interesting question when you are outside of a research lab. So it's one thing if you're in a cage system, you can have some controllers or tablets, but if you're out in the field and you have to carry this with you, you probably don't want to carry around a pair of live controllers on your belt. You want something very small and very lightweight, but it also has to work well. So I think that's it's an interesting and open question. I'm happy to hear any ideas you have about that later as well.
Yeah,
Sure. Okay.
Barrett, great talk. I I was really interested in the idea of designing information spaces, so changing the design of buildings or workspaces. What sort of, have you had any more concrete thoughts about what sort of changes you might have?
You sort of an immersive visual
Yeah,
analytics
so
space?
yeah.
No, not really. I think so it's interesting to look at making something configurable for a certain task. You want to kind of have like a modular space where you can say, okay, I want this kind of visualization here. This is going to be for multiple people, kind of we want a large display type thing, and we want to have an assortment of certain visualizations, but also taking advantage of this kind of spatial principle where maybe if you have a larger visualization, you can kind of use that memory to say, okay, I thought I saw something interesting over in this area, and you can help use your spatial memory to guide you to where you saw that. Kind of like when you're doing a jigsaw puzzle. You remember, oh, I saw that piece, it was over here somewhere, right? And maybe this will work on a larger analytics scale, but also, you know, there's questions about how this should be configured. If you have multiple people working, you don't want to, you know, be bumping into other people. So there's a lot of research that has shown that people can be very territorial. For instance, on tabletop systems, people arrange things into, there's a public space, this is our workspace, this is our kind of scratch pad where we're in progress, and this is kind of my personal space. And people just, without even talking about it, they just naturally don't reach into other people's personal spaces. So how does that work in a 3D immersive environment? I think is an interesting question, but I'm not sure if it really approached yet. So, you know, so I think there's a few dimensions to that. So how can we kind of provide these prefabs to easily build these configurable environments, and then what are the constraints on the type of arrangements that we can build so that they're useful?
Seeing as you have a background in music, have you done any work in the role of sound in specialized information communication?
No, that's in information visualization. No, that's actually a really interesting area I haven't thought of. I did a few kind of pet projects during my graduate work. So I did stuff like, you know, like an optical flow motion controller for like improvisation with this improvisational ensemble and things like that. But no, I actually haven't thought about applying it to crossing that over into InfoVis. But I think that's it's an interesting idea. So can you, so in particular, so say in this IV scenario where you have data flowing through these pipes, maybe you can be directed to important, like maybe you can find a bug by listening to where data is making a specific sound or something. So it's a very good topic.
Other questions? Okay, let's thank Barrett again for a great This is going to be around for the rest of today, so if you'd like to meet him, and I know a couple of you have sort of organised to do that later in the day,